Okay, this is just a short follow-up video from last week where I left some questions hanging about your opinions on how long would it take for certain things to do. The first question was, how would you like to write out the different ways of putting the letters random, R-A-N-D-O-M, down? And you should quite quickly realise that there's a lot of ways that this would come down. It would take you a long, long, long time. If you actually watch the longer video, the second video on arrangements, there are 6 letters. That means that I've got 6 choices for the first letter. And then next to that, I've got 5 choices for the second letter. Now, because if I take the R in the first place, that means I've got A-N-D-O-N left. Now, the question is, how do I combine these numbers? Well, with what we're saying is I could choose 6 things first, and then following that, any of the other 5. That gives me a total of 30 different things I could have. I could have R and A, I could have R and M, R and D, R and O, R and M. That would give me, for the first choice of R, 5 options. Then if I change it to A first, I've got A and R, then A and N, A and D, A and O, A and M. So the R would give me 4 choices. It would give me 5 choices for the second letter. A would give me 5 choices for the next letter. N would give me 5 choices for the next letter. D would give me 5 choices for the next letter. O would give me another 5, and M would give me another 5. That's why we've got 6 choices for the first one, giving us times 5 to give us 30 choices for the first 2 letters. Keep going. We've got 4 choices for the third letter, 3 choices left over for the fourth letter, 2 choices for the fifth letter, and the last letter, whatever's left, must go in. And that was written as 6 factorial, or some people write arrangements of 6. And that 6 can be written in a number of different places. So let's put in the 6 factorial. 6. In fact, is the little exclamation mark, which there it is on this one. It's there near the logic button, this button. So I have to get the shift, an exclamation. And a few people were, I've seen them put comments in. And there are 720 different ways of writing the letters R-A-N-D-O-M. So if I asked you to write them all out, you're going to be there for most of the day, probably, but working them out. Here comes the really surprising one. And I think it was Thomas actually gave me the proper number for this. I'm not sure she understood quite how big this number is, and that's why I said this is the magic of playing cards. If we have 52 different cards, again, choices are to do 52 cards. We've got 52 choices for the first one. So the arrangements of 52 is going to be 52 for the first choices, times 51 second choices, times 50 third choices, times 49, and keep going all the way down until all the cards have been selected and we're left with the last one on its own. And that, and if you type it in, is 52 factorial. Now, 52 is not a particularly large number, but this is the world of probabilities and arrangements. This is what leads to the world of quantum mechanics being so weird, is how big, what happens with these numbers. This 52 factorial is actually this number. Now, a lot of you won't really understand fully what this number means. This says 8.0658. I'll leave the other digits, but it's this last part. This little bit down there says times 10 to the 67. So this bit is not a decimal number. what it's got to do is multiply by 10 to the 67. And if you remember all those indices chapters that we keep having to do, 10 to the 67 means you've got the previous number multiplied by 1 with 67 zeros on it. We've got 67 zeros on the end. Now, it doesn't mean that it's 80658 and they're 67 zeros. It means this 8 has 67 places following it. So there are 68 digits in this number. And I'm going to do a little thought experiment with you about how big is this number. First of all, let's say there are 7.5 billion people in the world. 7.5, and a billion is times 10 to the 9. So that's a billion people. Roughly the population at the moment. So we've got to divide that by 7.5 times 10 to the 9. That's divided by 7.5 exp 9 is that times 10 to the 9 bit. So this is going to come down to 58. So that now means if every single person had a deck of cards, that each person would have 10 to the 58 arrangements they'd need to make. Let's think of another fairly big number. Well, the universe, and we're now just going to work in round numbers, is about 14 billion years old. So we're going to divide that by 14 times 10 to the 9. And now we're getting to 7.7 times 10 to the 47. So that is every person in the world for every year. Well, let's try and get that down to seconds then. So to convert years to seconds, we have 365. If you want to be even a bit more accurate, 365.25 days. That's 2 times 10 to the 45 days. So that's every person for every day that the universe has existed. Let's go from days into hours. So divide by 24. Divide that by the number of minutes. And divide by the number of seconds. So we're now going to convert this into people per second since the start of the universe. So this now says there are 2.4 times 10 to the 40 people per second. So if every person, this is how much is left over at the moment from what we've been doing. We have 2.4 times 10 to the 40 things that need to be done by every single person for every single second that the universe has been happening. And we're talking about trying to make orders of cards. So we're saying how many shuffles people have to do. We're nowhere near there yet. But let's keep going. Upper limit here, this is the number of stars in our current galaxy. That's about 400 billion. So let's divide this by every single star. So 400, a billion is the exp to the power of 9. And that says that for every single planet, every single star in our solar system, we have 6.1 times 10 to the 28 So that's people on each star per second of the universe they would have to make this many shuffles to actually be getting close to the number of cards that we have. Let's go one more. We'll assume how many galaxies are there. So the galaxies in the observable universe. And that's going to be in the billions as well. Right, trillion is 10 to the 12. Oh, we're going to take a big load of numbers off this now. So we've got 2 trillion galaxies. So divide that number. So this is getting in the way. So we need to divide by 2 trillion. So that's 2 to the power of, times 10 to the power of 12. American trillion I'm going with. And that says I've got 3 times 10 to the 9. 3 times 10 to the 16 stars in the universe. Per second. So assuming that every single star in the observable universe has 7 billion people living around it, and we went from the start of the universe counting in seconds, and every single second people make a perfectly random shuffle, we're still only 1 quadrillionth of the way there. We have done nowhere near enough shuffles. So every time you shuffle a deck of cards, if you have shuffled it fairly and it started off reasonably random, you would have done something unique. So shuffle a deck of cards to do something unique today. Little question for you is, what is the best shuffling method? And I'll tell you, it's not any of the ones you normally would think of. How would you, what's the best shuffling method? Go and have a look online and see what people are saying. Okay guys, so that's just a little warm up following on from last week.